Admit. How do I admit people? Okay. All right. All right. Let's see if I can just go like this. Okay. All right. So today, okay. Hello, my name is Kyle Dampier. Since we lost a couple minutes in the beginning, if you have any questions about me and my background, you can figure out. You can come and ask me after the presentation. So I'm just going to get started. We have a lot to talk about today. So first in the agenda, we're going to be talking about for about 5 or 7 minutes about what exactly what is a neural network and what does it do? Why is it powerful? And why can it literally fit almost any function that you throw at it? Next, we're going to be talking about what is a convolution? How do convolutions work and what do they, why are they helpful for say, processing not just an image, but stuff like time data or stuff that has a sequence. Third, we are going to be talking about how you can find and collect your own data to train your models. And then finally, we're going to be talking about this thing called an image generator, and we're going to be coding through it. And I'm going to tell you guys how they work and how you can like shift images and make it kind of more, I guess, fit for your model. And then we're going to be talking about how we construct our first CNN. Not this CNN. It's called a convolutional neural network. There's 2 main parts to that. There's the convolutions and the neural networks. But today I'm going to be starting with the neural network first because I think that's a very important part. I won't be going very deep into this, but I'm sure you guys have seen this before. Neural network. It's like, what does that actually mean? It doesn't really mean anything to me right now. But if you haven't seen this before, this is a very good thing, and I promise by the end of this, you will know what's going on with neural networks. What?
I'm just gonna pin the video so
okay.
It doesn't interrupt your screen.
Okay, awesome. Okay, so have you guys seen this before? Wait, shoot. So let's kind of break this down. There's the inputs to the function, and there's the outputs to the function. So you basically have this like list of inputs X that you want to be able to fit a function F that takes in these sort of like whatever you sort of put as your X, you want to produce some Y. And if you replace X with inputs and Y with outputs, that's what you're doing. What you're doing with the neural network is you're finding a way to create a function F that fits your inputs into an output. So for example, an image can be broken down into a sequence of numbers, like an array or like a list of numbers between 0 and 255. We will talk about that later. Why is this not working? Okay. So the lines on this graph here, I don't know if you guys can see it. So the lines on this graph, the W's mean the weights, and you multiply weights on the lines. It helps scale the function up or down so it helps you fit the data. So it will look somewhat like this within the function. The red circle is the bias. The bias is also trained. This helps shift the function left and right so it can fit your data. And now to put it all together, we have this function with the weights X and the bias B that produce an output Y. So does that make sense to everybody? Awesome. Okay. So now we have this activation function. What function are we actually going to fit to this data? So if you want to fit this data, you can do a bunch of different types of these functions where we, instead of doing like just a line, you can do like a sine wave or a cosine wave or pretty much any function that you want to fit. Okay. So now we have the whole picture. We can see that these weights and biases are all being added together into this like summation function that is then all fit through this sort of activation function. And you produce this output Y. So there we go. We can change this F to whatever we want later, and I will show you guys how to change that in TensorFlow. So here's like the overall, what we've talked about. The output, the Y prediction is in these green brackets. Okay, so we talked about that. So here's a linear activation function. If we wanted to do a activation function on just something that was linear, we use something like this. And instead of saying like an active, so when you're training, we more use the term like a regression when it's unsupervised. When it's supervised, we like the term activation function. So we have this. So does that make sense to everybody? But we also have all these different types of functions. We have these rectified linear unit, which takes the max between 0 and the same z, or like whatever it actually is. We have tan h, which can scale between -1 and 1. And we have a sigmoid, which is between 0 and 1. So that would be, so the 0 and 1 would be really good for Boolean values. But if you wanted to say, like scale something based off of something else, you would use like a tan h. Why is this not working? Okay, so there's a bunch of these functions, and you can even make your own in TensorFlow. You can create your own activation function, and it will work. Why does this never work? Okay, so changing the weights, kind of say you were to do this on a sigmoid, changing the weight on the sigmoid would look something like this, where if you were to sort of make the weight higher or make the weight lower, it would kind of move the function to sort of fit your data. And so when you change the bias on these functions, it would kind of shift your function left or right based off of however big your bias is. So basically, if you have all this data and you want to find the patterns in it, you can pretty much take any type of function you want and fit to this data. So here's what it kind of looks like. Yeah. If you go here, I actually have a demo. So this function here, sigmoid, I think, yeah. If you were to change the weights, it would look something like that. And if you were to change the biases, see how when it goes to negative, it changes the direction of it. And if you were to change the bias, say make this 1, there, you can see how it shifts the function left and right based off of like, oh, whatever your data is. Okay, and this works the same for the tan h, and it works the same for a rectified linear unit. So if I were to just start animating this will look crazy, but so you can kind of see how they change and over time and what's kind of happening. So you can basically fit pretty much any function to this type of data. So let me go back. We have this slideshow. Let me see. So that's all cool. I'm going to show you guys how, like, we don't have a lot of time, but I'm going to kind of skip through this video a little bit. But you can see what he's doing is he's taking a bunch of rectified linear unit functions, and he's going to try and fit a cosine function to it. No, a sine function. So we can see over time, because he has 2 layers, it allows him to fit this function based off of different values for the weights and the biases. So you can pretty much figure out, like, you can pretty much fit any function you want. It's kind of crazy. So now you kind of get the whole picture of what's going on in like a neural network and why it's important to have these sorts of things, and like what an activation function is and everything, and what weights are and what biases do. What are convolutions? So a convolution, so so basically all an image is it's just a 2D array of numbers between 0 and 255. If we scale that between 0 and 1, we have now an array of numbers between 0 and 1. And now we can throw that into a neural network and hope something goes well. But that won't really work well, and it's not really cost effective on the computer. So what we want to do is break down the image more, basically like take that sort of image, break it down, sort of find all the really important parts of the image, like all the edges or all the like contours of like what's going on in the image, all the color changes where like those are happening. And we basically want to, I'm going way past this. And we basically want to create this thing called a kernel, where it swipes through and it finds like I guess like an average, or it would like do like multiplications of things pixel by pixel. So it would go like sort of like all the way through the pixel. So if we have this example here, so if we have this convolution or filter here, where we have the ones on the left side and the negative ones on the right side, the output of this would be for each of these things here. So like this output here would start with this one, and then this next output would be over here. So say we add 3, 1, and 2 together, that's 6. And then we got 1, 7, and 5, that's negative 13. 6 plus negative 13 is negative 7, and that's the output. So something like this. So what does something like this look familiar? It looks familiar because those weights, instead of treating those weights as like, so instead of you going through and picking those types of values, the whole thing about a convolutional neural network is that it finds the most optimal values for those convolutions already. And so basically those, all the stuff in this sort of matrix then becomes a weight that you can train within your model. Okay, so here's an example of a cool thing that you can do with convolutions, and it's called like, where like you can take like all the important parts of the image out. So here's an example of one. So here's like an animation of how the math is being done. So you can see same sort of deal. You have all these numbers being multiplied by like whatever numbers in this matrix, and then you sum them all up, and then you get your final value. But something like this would look like this, where you have all these values, and it would output, and it would go through, and it would create this kernel that goes and calculates a brand new image based off of an old image, and it basically takes all the important stuff out of that image. So there we go. So that's what a convolution is. So now that we're here, so machine learning, if we were to do just machine learning, there's 2 main layers to this. There's the convolution layer, and then there's the neural network layer. The convolution layer, when you're doing a machine learning, is mostly done. So like something for like a medical equipment or something like that, they would create their own convolutions for like stuff like a bone imager, or like looking at cells and stuff like that. However, if we have like an image of like a dog, there's not really a set in stone good convolution to do that. So what they do is they take the output from these convolutions and throw it into a neural network, and then they can do a classification that way. But now, deep learning, we have the feature extraction and both of the feature extraction and the classification are being determined by the computer. So it's like being solved like the way it should. Okay, so here, what does this do? So the convolution and the ReLU. So the convolution is basically just taking like a bunch of these different values and trying to find. So I have time to talk about this, but all the weights inside of the convolution are also used in backpropagation. So whenever you have like a convolutional neural network, it finds all the entropy in the data, and it finds like the sort of matrix that sort of I'm sorry. It finds the matrix that will determine the most amount of entropy in that system, and that's what your filters are. So like it decreases the amount of it tries to take the least amount of data possible. Okay, so there are pre-trained networks. Oh yeah, and then a max pooling. Well, I'll talk about that later. I don't have time right now. So let's go on to the next one. Why does this keep not working? So here are some examples of pre-trained models. We have like VGG19. We have Inception v3, which is Google, and ResNet 50, which is also Google. VGG19 is open source. You can go and download it. They actually encourage you to download it. And I actually put a picture of a dog through VGG19, and I got this. And so you can see like the convolution that they created. So this was trained on, let me go back. This was trained on 1 million images with 1,000 different objects. So that's a lot of data. And basically these convolutions are really good for having like different types of so like say you want to do like a dog, but you don't want to like create a convolution for how to throw it into your machine learning model. You just want to have like a pre-trained sort of convolution that works. You can go and download these and use them in your own code. Okay, so let's go down. So how do you guys find and collect images? I'm a big fan of Kaggle. I go on to Kaggle all the time. I think that's like what I do in my free time is I just like going on Kaggle, looking at data sets and finding like cool patterns and stuff in it. And also search engines. You can just search for dog on Google. And a really cool demo that I have really quick. Oh, shoot. Let's see if it's here. Oh, well, there's this cool extension called Image Downloader that allows you to take all the things that are like a sort of image on a website and download all of them to your PC. And you can sort of categorize them by whatever you search for on Google and it'll work. And you can also use Selenium, where you can just go in there and have like the DOM, and you can just take out all the stuff that are images, filter out like profile pictures, logos and stuff like that, and then just take the actual content from it. Or you can go and create your own data set. You can go out there, say you wanted like a model that would take like a picture of a car and predict what brand it is, go and take a picture of a bunch of cars and put them in folders of what the brands are, and then you can create a model from that. And so now let's talk about image generators. Okay, so if you guys want the slides, you guys, I'll leave this up for a little bit. If you guys want the slides, you can go and get the slides. My GitHub, I do not have very many notebooks on there right now because most of it's on Kaggle, but I will, after this, I will go and upload a bunch of my notebooks that I've been working on to my GitHub. And then, oh, here. Are you guys good? Good? Awesome. All right. So here's the collab. This is the project that I'm working on. This will work out of the box. You don't need to import anything. You don't need to do anything except the files, the data that I have is hosted on my content delivery network. So I am paying for that. So after the end of this month, that will no longer be available. So yeah, let's code. Oh yeah, and a very important thing to note as well, to execute a cell, you just hit Shift and return or Shift and enter if you're on Windows. All right, so now that we're here, so this right here will download all the data to the folder, and then you can unzip the data that it downloaded here, and then that will give you this folder right here, this natural images, where it has just a bunch of pictures of airplanes, cars, cats, dogs, flowers, fruits, and stuff like that. So after you doing that, you can import these files here, or these libraries. So Matplotlib is really popular, NumPy is really popular, Pandas, and the main one we're going to be talking about here is Tensorflow, which is the topic of today's discussion. And Tensorflow gives you this class that's really useful. It's called an image data generator. And what it allows you to do is create these things where you can like add like rotations and stuff. Oh, hold on. No. 2, 3. Oh, here it is. Okay, where you can like go in here and you can see like if you wanted to add like random shifts, you can shift your sort of image around in the actual thing. You can randomly flip your image. You can make the image more bright or less bright. You can make the image zoom in more, zoom out more, and so on. So what I did here was I just added some shifting to this. Let me go here. So I just added like a little bit of rotation. I changed the width a little bit, changed the height a little bit. I flipped it on its horizontal axis, so it would be like this way. And then I rescaled all the data that came in. I just divided it by 255, which is the because each pixel is between 0 and 255. So it makes it between 0 and 1. And then I add a shear range, which just moves the image. And then I added a zoom range. And then I did a validation split. So this right here, this means that 20% of your data set is validation, and that for training, you use 80% of your data set. Okay, so I go here. I chose 256 by 256 image size. You can go in here and change it to whatever you want. I actually encourage you guys to go to go into this and change these values and see if you guys can get better scores than me, because I kind of just put random numbers in, to be honest. I didn't really go too hard on thinking about what would be really good for these. But yeah, essentially then you can just flow from a directory and you just input that directory, and then each of the subfolders inside of that directory are considered that class or like that category. So like that's what you're sort of generating. So like all the images inside of the airplane folder will be generated and randomly shifted, moved, rotated all throughout. And you can sort of generate different images from basically just like a directory structure, which is super easy and most people can figure out. And like you can give to like a 5-year-old to say, go and take a bunch of pictures of flowers and please categorize them. Thank you. And basically what comes out is something like this, where you have like pictures of cars in a square that are resized, and you can see like they're moved left and right and everything. And you can go in here and like there's planes, cars, flowers, all that stuff. So, I was gonna do why my screen is frozen. Yeah. Oh, there it is. Okay. So, I'm just gonna delete that. So the base case for this, this is not the base case, but I was gonna show you guys VGG19, but you can just go on. There's a bunch of examples of people using VGG19. So I wanted to show you guys how to make a sequential model in keras. So this basic model here. So to visualize this, let's go back. I actually did a custom visualization for this model in Figma, so you guys can see how it's kind of working. So in this convolution here, I'm just going to do it here. In this convolution, it starts out with a 256 by 256 by 3, because that's RGB, red, green, blue matrix. And then it has 32 5 by 5 filters, and it filters through and it gets you then a 252 by 252 by 32, which the 32 is just all the different filters that are in there. And so it basically gives you 32 different generated images that kind of allow you to send off to the next layer, and then those will generate 32 more images and then 16 more images. So the next layer here, oh yeah, and then we have an average pooling, which just takes like a 2 by 2 square, takes the average of all the values inside of that square, and which is really good for things like an image, because it kind of acts like a blur. Like it kind of just makes it like it does like an average instead of like something like a max pool, where like if you're doing stock data, a max pooling would be a lot better. So yeah, so you just have your input image, and then you have your second layer, which takes your old layer, which is 126 by 126 by 32, and then it creates a new. I think I changed these values from 64 to 32, but basically, you guys get the idea. Is it's scaling down these values, and then it's normalizing them after each set, which means that it's taking, like, if it's a really high value, it's 1, and if it's a really low value, it's 0. Okay, so now we have the main sequence. So this is what it looks like. It's kind of scaled. It's not really too scaled, but you can kind of see what's going on. You have this huge image. It's taking it down a bit. It's finding like all the features inside of that image. It's taking it down again and finding all those features, normalizing it, sending it to the next layer. And then by the end, we're flattening out these convolutions, and then we're throwing it into a neural network with a bunch of hidden layers. Well, in this case, 3 hidden layers, because the last layer is the layer that we're going to use a softmax on. So the activation functions that I put in there, and the number of weights between the all the values I also put in there. So you can see here. Yeah, so let's just code this out. Sorry if I'm staying late. Oh no, we will be good. So basically, we can take this layer. So there's this thing in Tensorflow called sequential, which basically allows you to just go step by step and train your models based off of like some sort of pipeline, right? Where all you would have to do is just input this stuff, and then it is able to generate a function that fits to that input to generate some output. And so this is literally all we have to do. We have our first convolution, which has 32 filters. It's a 5x5 kernel, and you can say that the input shape is whatever the image shape is here, which comes from right here, this image size, or this train generator. Okay, so now that we're here, we just add an average pooling 2 by 2. And then after each layer, we do normalization, which allows us to scale the data between 0 and 1, which makes it a lot easier for the like network to understand like what values are really high and what values are really low. Because instead you could have like a bunch of negative numbers, which means something else. But if you don't have that sort of like a normalization step where it changes it between 0 and 1, your like networks afterwards, they're not going to be as accurate because it's not the same between each step, if that makes sense. Okay, and then we just add 3 of these layers. We add a convolution here, and then we do average pooling, batch normalization. So, and then here we just add this layer called flatten, and we are able to flatten out the I guess it was, what was it? The 16 by, I think it was like 30 by 30 matrix into like this 1D array, which we can throw into a dense layer, which is the actual neural network, or where like the sort of activation functions are being fit. And I did, 256, 612. And then at the end where we have, and I use a ReLU for this activation function. And at the last layer, I used a softmax, which basically just takes like, it creates like a probability. So like if you were to do like a normal max or like like some sort of like a categorization thing, it would be either 0 or 1. But what I wanted to do instead was use a softmax, where it gives like, I guess, like a probability of like what the model thought each thing was. And then we just take this model, like this model that we say to compile it. Our optimizer, which is like how we're doing our back propagation and everything. I'm just going to say that we use Atom. We have categorical cross entropy as our loss. I can go into that, but that's for another time. And then we also have a metric that is called accuracy, which was something that like I felt like I could understand what was going on, because like the loss for the categorical cross entropy, like it makes sense, but it's like it's not really a good indication of like how well your model is actually doing. So I just added another metric called accuracy. And you can see here on the model, we can just call the summary, and it'll tell you what the output shapes and how many parameters are in each thing. As you can see, this one dense layer has 14 million parameters, because each input has to go into its own has to go into 1,024 different layers, and that 1,024 different weights it has to train for that one pixel and that one image. And you do that over and over again, and it builds up really fast. And then this dropout layer basically just drops out of some parts of the neural network. So it'll randomly get rid of, I think, 20% of the network, because we don't want the network being really reliant on like some specific value within that neural network, because what can happen is like there can be one node, I guess, that has like a super high, like 2,500 of value, and then the rest of them are just all 0. But if you add dropout and that one becomes 0, like here and there, then like there's that it really helps just to kind of like make all the values inside your neural network more even, if that makes sense. We want you to distribute all these values as evenly as possible. Okay, and now that we're here, we have these callbacks, which this one here is early stop, where it stops when the validation loss stops going down, and its patience is 5. So after the validation loss hasn't gone down 5 times in a row, it just stops the model training. That's a useful callback. Reduce the learning rate on plateau basically allows you to monitor the loss inside of your function. And when your loss starts to plateau, or it doesn't really or begins to not do any better while it's training, it will decrease the loss so it can get a little bit higher up in accuracy. And then I added this callback called model checkpoint, which whenever the validation loss is at its highest, it saves it to this file called basicmodel.h, and it prints when it saves it. And yeah, so if you want to monitor something other than validation loss, you can. If you want to monitor accuracy, whatever you want to do. If you want to do accuracy, you would have to change this mode to be min, and it's already, I think it defaults to max, but yeah. So then we just call basic model.fit, and then we can see we start out with a 50% accuracy, but as we go through our different data sets, we get better and better. And then at the end, we are looking at about, after 20 epochs, we're looking at about 74% accuracy. You can save this model afterwards. I do it as convention. And then let me see if this is going to work. Evaluate. Is this running right now? Oh, it is. Nice. Okay. Awesome. Now I can show you guys the demo. So what I did here was I just wrote a little bit of code that takes in any a picture URL, I guess you could say. And so I'm going to do this one first, where it takes in a picture URL. So this is of a dog, or no, of a cat. And then it outputs a prediction, which is the array of values. So this is the array of what it thought the thing was. And so you can see the highest one here. So it between cat and dog, it's hard to tell, right? So it can't, it's sure it's not an airplane, but between cat and dog, it's a little bit, it's uncertain. So it says 47% sure that it's that it's a cat. So let me go. Well, my screen is frozen. Okay, there we go. Stop. That's my natural language processing team. Yeah, so then the max is there. The argument max is 1. And when you go back to our generator, the 1 was a car. Wait, no, sorry. Wait, yeah, what the heck? Prediction, I guess it guessed it wrong. Oh, well, happens. How about we try another one? There's different categories, but again, I put random values into this thing. You guys, I encourage you guys to go to this notebook that I have on my slides and go and change the values, add some layers, find stuff that you think would help. Go and find stuff that you think would help make the model better. So let's try this one. So that one didn't work. My last model that worked, so that's unfortunate. But well, I mean, you could see that it thought it was a cat right here. It was, this one was a cat, this one was a dog. So let's go back. Yeah, this one was a cat. So apparently cats are cars now. Yeah, so this is a dog. And then the prediction outputs, what is it? Prediction.max, argmax, 5, fruit. Oh, what the heck? Why did it? I swear this is working before. Why is this? Huh. Yeah, that's a hiccup. I should have loaded in the model. Oh yeah, also how to load in models. Forgot to mention this. So if you have a model that you already have and say you want to deploy a model, normally, so if you wanted to say deploy a model, you would say the file path, and then you would just say tf.keras.models.load models, and then you just say the path of the model, and then this will act as the same as this object here, this basic model object. So it just holds all the weights and the biases. I can't believe my demo didn't work. That's so annoying. It was literally working right before I came in here. I tried it and like I showed it to Justin. He was like, "Oh my God, stop. Why is my computer like this?" Okay, let's try one more time. Why is it taking forever? Whatever. Yes, of course. Oh yeah. Any questions? I'm sorry. I'm just really mad that my thing it was working right before I came in here. I'm just it's okay. It's fine. Yeah. What's up?
Said, like, you were encouraging us to like check out the slides and try out different like I guess parameters to try and make the models better. Like, what guides that?
What guides that?
Like, how can you guess what will possibly make something better?
Well, so something that I guess you could do is like so there's something called TensorBoard where you can view like where you have these things. So these things that we like the stuff that we put in like the different layers are called hyperparameters, and the TensorBoard can track the loss and accuracy over time based off of whatever hyperparameters you put in for that model. So like if you want to change like one of the convolution layers and you put it into like this TensorBoard, then you can see like how the loss and the accuracy changed over time based off of what your hyperparameters were.
Okay, that makes sense. But I guess there's no sort of knowledge of like why.
Well, this is brand new. The paper that came out on convolutional neural, like the landmark paper that came out on convolutional neural networks like this came out in 2018. Or wait, no, 2007. 2018 was Transformers. So in 2007, so there's only been like this has really only been a thing for like I can't do math, like 15 years. So like there's a lot of stuff that we don't know about this, and again, I encourage you guys to go and find out for yourself, like what do you think you could change in the neural network that would make it better, or like what do you think? And if you guys want, I'll put this back up. I'll put this. You guys want the slides of the GitHub? If you guys want it. But yeah, I really do. I encourage you guys to go in here and try it out. What? Yeah. Well, yeah. No, I guess if you guys get the slides, you have contact. I'm pretty sure you can get all these links from the slides. So, all right. Any more questions? What's up?
I have a question about bias. I was a little confused about it. So just because I'm thinking like all of this work is to judge the shape or judge the trend of bias seems like something that you manually enter. So is it really just like as you look at the graph or like,
yeah. So the bias is calculated. So when you do back propagation, you do this thing called a differentiation. And you know how in calculus, when you solved for the area under the curve, where it's like the plus C, that's what the bias is basically, is it kind of allows you to, it's hard to explain without telling you what auto differentiation is and how back propagation works. But essentially what bias is it's like, it's kind of like like if you have like a line sort of mx plus b, where that b is, where it kind of starts in the graph. Yeah, no problem. What's up?
I know two of the common frameworks are PyTorch and TensorFlow. Is there a reason that you tend to prefer TensorFlow over PyTorch?
Yeah, so I actually prefer PyTorch, but when I'm teaching it like a grand overview of like what it is, TensorFlow is a lot easier for people to read the code and understand, because PyTorch is very like matrix calculation, very very code intensive. And like in PyTorch, when you have calculations of like a large matrix, you can like tell it to like either use the GPU or the CPU. Like it's very in depth, but in something like TensorFlow, it just does all that for you, which is great. And that's why I prefer PyTorch for my own research, but when you're first starting out and learning about the layers and what they do and how they work, I think TensorFlow is a great start. Yes, welcome, of course. Any more questions?
is there any talk of using this in a legal sense, like hash imaging used to?
Yes. So this is actually attacking the P versus NP problem, where you have like cryptography and you say you wanted to take an input and create an output. Neural networks are functions. So you can like, so since for every function, there's one input and one output, you can essentially go back in the function. So like say you have a hash and you could again, based off the neural network, you could solve for what that function actually kind of is creating, which is crazy. So this will, I think personally, this will cause issues in cryptography. But the thing about cryptography is that to make it like more secure, all you have to do is just add an extra bit or add an extra byte. And like instead of 256, use a 512-bit encryption, and it's like exponentially harder. So it will cause a problem, but I don't think it will affect us personally. Yes.
How do you optimize the number of layers to balance computational efficiency with still like an accurate network?
Okay, so that goes back to it's all in like what you think is reasonable. Like you could take out 3 of the layers, and if you only want like a 50% accuracy on the data, you could take out all the layers and have a really fast have a really fast convolution in a neural network, and it could basically like work like that. It's up to you. I know I don't think TensorBoard tracks time, but there's a tool called weights and biases, WNB.com, where you can go on and it'll track how many epochs over time. So you can track how fast your model is going. But other than like, there's no way all the balancing act stuff that you have to do with a neural network is done by the developer. Does that answer your question? It doesn't really answer your question, but it's just, there's no real answer to your question, which is, I'm sure there's going to be papers coming out soon about that though. Yes, no worries. Anybody else? Yes.
I wondered, when I try to access the notebook, I think it says that like I need to select.
Oh, you do? Thank you. Hold on. Let me make sure. Link. Change to anyone with the link. Okay, now try it.
I was gonna ask, what is this, Google Drive?
Oh yeah, this is Google Colab. I'm a Google Colab Pro person. That Google Colab Pro allows you to use GPUs whenever you want to use GPUs. So like here, I can go and change the runtime type, and if I'm doing something like graphics processing, I can use a GPU, and if I'm doing something like a natural language processing, I can use a tensor processing unit, which is a TPU. And so yeah, it's basically like you can upload. You can basically go on your drive, upload a notebook, and when you click on it in your drive in the URL, it'll open up in Colab. Yeah, it's completely free. Yes. Yeah, it's not free for the GPUs. It's like $5 a month or something. It's like nothing. And you can basically go on there and do whatever you want. Yep. Colab is free. Any other questions? Yes, ma'am.
So how do you choose the best sort of activation function for a specific model? I know that most of these
Yeah.
are versus when would you use the sigmoid function?
Okay, so something for like a sigmoid function. So a really good way to answer that is it depends on the application. It depends what you're trying to do. So like something like a rectified linear unit would be a lot better for something that's like trying to fit like really weird functions. But if you're trying to say fit a like say you're doing stuff on music, using something like a cosine function or a sine function would be a lot more sort of advantageous for your cause than something like a linear function, because you would need a lot more layers of linear functions than you would like just one single cosine function and changing the weights and biases of that. But it really does depend on whatever you're using. Most people in practice use ReLUs, which is the rectified linear units, because it's just very versatile and makes sense. Yeah. No worries. All right. Of course. Thank you guys. All this stuff. Oh yeah, if you guys want, I do stream on Mondays. I try and stream on Mondays for the Gator Club here at UF. I think a couple weeks ago, I did a stream on time series forecasting, and I talked about recurrent neural networks, which is like neural networks, but for trying to predict recurrent functions instead of like normal functions. All right. Thank you guys. I appreciate it. Share.